Okay, so someone has to mute. Okay, all right. So let's get started. Let's continue where we left off. The next option is feature encoding. So we have done we have checked for missing values, checked for column data types, irregular values we don't have, but nevertheless we have to check. Okay, duplicate rows also we don't have. We barely have 157 rows, but you have to check for duplicate rows also. Feature engineering we have done. We created a column called age out of the launch date column. Outlier we have done. Encoding is what we have. Transformation also we have done. Scaling and normalization we'll see again. Feature selection also we will see. Now we are looking at encoding. Okay, so in encoding part, okay, encoding has to be done basis on the type of variable. If your variable is ordinal, okay, it follows certain order, then you have to do certain type of encoding. Okay, so that is what we have. I think this is what we discussed. For ordinal variables, you have to do the encoding in certain way, and for nominal variables, you have to do the encoding in certain way. Okay, so that encoding, here it is. So this we already went through encoding part. So you have to be aware of which encoding has to be used when. Okay, we can't blindly go ahead with one hot encoding, or we can't blindly go ahead with label encoding. Okay, it all depends on the type of variable. Now after encoding, now while we talk about this encoding, you have to ensure there is something called cardinality. Cardinality means different type of values that a feature can take. For example, let's talk about this manufacturer. Now this manufacturer alone, there are more than 1,000 plus, or even more, I don't know, 1,000 plus manufacturers in the world. Okay, although your data has only 157 rows, you may come across in the new data, if you may get data on new manufacturer, okay, which is not seen by your model. So cardinality has to be handled. So how will you handle the cardinality? Okay, cardinality first of all means number of unique values in a feature. Okay, for high cardinality, if the cardinality is high, then you have to start bucketing the values. Okay, for example, in the manufacturer example, the way how you can bucket them is the manufacturers that manufacture luxury vehicles, the manufacturers that manufacture maybe sedans, with the manufacturer that manufacture between vehicles between certain price range. Okay, that way, basis on one of those categories, okay, you have to start bucketing them. Okay, that is how you can handle. For loan approval example, another example I'll give you. There is a feature called occupation. I think we have talked about this as well. So for occupation, the way how you will bucket is high income drawing employees to be in one bucket, medium or average income drawing employees to be under another bucket, and low income based occupations to be under another bucket. So that way what will happen is, see, you with cardinality you still can't tell who is going to default. Okay, that is not the purpose of cardinality. The purpose of cardinality is tomorrow, if in the new data you get a value that is not there in the training, now what you can do is you can immediately look at the income of the customer, and you can automatically assign a value. What I'm trying to say is, for occupation or maybe manufacturer only, I'll take. For manufacturer example, Audi BMW, Mercedes. So these manufacture vehicles of above 50 to 60 lakhs only. Okay, so they should be bucketed as luxury vehicle manufacturer. Okay, so let's just say you have another manufacturers, like you have Tata, let's just say Toyota. Okay,
Honda.
let's just say
Honda. Toyota, Honda, Hyundai.
Mitsubishi, Hyundai, yeah, Mitsubishi, pardon my spellings if I'm typing something wrong. Okay, then you have Honda, then Hyundai. These can be bucketed into another category, like for the lack of middle class vehicle manufacturer, or maybe middle segment, something like that, means middle segment vehicle manufacturer. Okay, now how will you do the next question is, how will you do the encoding? The encoding has to be done. Let Mercedes, because this takes high price, so this will take as 3, this will take as value as 2, and let's just say Tata, I'm not degrading Tata, but I'm just for the sake of example only. Okay,
no, Suzuki, Tata,
yeah, sure, Mahindra, Tata, whatever. So this is, let's just say 1. Okay, this way you will bucket them. Tomorrow, where in the inference data, new data, if certain new value comes, okay, something that is not in this list, okay, something, can you give me a name?
Rolls-Royce.
Rolls-Royce.
What
will happen is, so what will happen is, the way how you will write the code is, we call them pre-processing script. Okay, I will tell you what that is in a bit, but what will happen is, when a new value like Rolls-Royce come, what should happen is, you should write a script in such a way that the price should be compared, and automatically based on the price, the value 3 should be assigned to it. Okay, for during inference, its price should be looked at. A simple function should be written with if condition. If price equals to exceeds this, then assign the value, encode this value, whatever value has come, as 3. So it will go automatically, inference value will be 3 here. Okay, now let's just say another value comes where price is none of these. Okay, price is none of these. Then what you can do is, another option is, you can simply assign the price as unknown category you can create first. Okay, first category is luxury vehicle manufacturer, middle segment manufacturer, low segment manufacturer. Fourth one is unknown segment. Okay, okay, maybe 0 or whatever the value you want to assign. So if the price is not matching one of all these 3, then it can directly be encoded as 0. This is how you will handle cardinality, and this is the only not the only, but the most used method. Okay, so by putting the values that are not seen prior, okay, which also don't follow any rules, to be in the unknown category. Okay, now feature encoding means, you know the definition already. Categorical value has to be assigned with numerical values. Okay, so now we already know for ordinal there is a order, so hence label encoding. Okay, nominal there is no order. hence one hot encoding. Okay. Discrete and continuous, they don't need encoding because they are already numbers. So this much, if you remember, this will be more than sufficient for you. Now the way how you can get on hot encoding is by two methods. One is sklearn has one hot encode method, and the other one is using get pandas method, using get dummies. Okay, so that is what we are doing here. We are one hot encoding the manufacturer. Why? Because there is no order in the manufacturer. Okay, so if you look at a manufacturer like Toyota, their costliest vehicle sells for 3 CR. Okay, and their cheapest vehicle also sells under 10 lakhs. There is a huge difference, right? 30 times difference. Likewise, the same can be said for Hyundai also. Okay, Hyundai also has Palisade something. I don't remember the name. Hyundai Palisade or something that sells. That's a luxury vehicle. Whereas cheapest also you have i10. Okay, same holds true for Tata. But if you are only going to talk about cars, then maybe Tata and Mahindra can sit into one category. But they have, all these manufacturers have their own sister companies, so that they that manufacture the high-end vehicles. So the point I'm trying to make is these manufacturers don't follow any order. Okay, hence they have to be one hot encoded. Okay, same holds true for vehicle type. All right, are you following me? Why we are doing one hot encoding here?
Yes.
Okay, next is target encoding or label encoding. Label encoding is done for a category where you have, I can just try here. Okay, so for example, vehicle type. One is fleet, another one is passenger. Okay, here also there is no order. Okay, so hence it's a categorical type, and here also you can do the one hot encoding. Third one, I mean, we don't have anything else, but if we had fuel type, there also we don't have any order. Let's look at owner, number of owners. You have first owner, second owner, third owner, fourth owner, and etc. So there you have an order. So for such features, you have to use label encoding. For label encoding, either you can directly call sklearn's label encoder, or you can use feature engine. In feature engine also there is a label encoder, or you can also do a manual mapping. Okay, you can just create a small dictionary. Okay, wherein which you are going to map. Okay, if for example first owner, let it get highest value. Okay, and second owner. Okay, this way second owner will get the next best value. So this way, if you create and start, and then what you can do is df of column you will call, and you will apply, or you will do a simple map of the dictionary. Okay, so when you map this dictionary, then automatically all the values in that column get the values whatever you have assigned in place of that string values. Okay, so this way also you can do 3 different ways to do the label encoding. Next, encoding. Once you do the encoding, now is the time for you to select the features. Now feature selection, you have to be very careful here. Okay, the first rudimentary way, very simplest also can be said, is a correlation. This we have already seen in data analysis, how to do it. Okay, and how to interpret it. So all you are going to do is just create this correlation, apply this correlation function on the data set. Okay, and when you do that, look at the scale. You have a scale from -1 to 1. Anything away from the 0 is what is to be concentrated on. Okay, if something is closer to 0, straight away understand that it's a useless feature. As simple as that. Okay, now our aim is to sale value. Sale value is sales in thousands, or whichever, whatever we are predicting. We are predicting sales in thousands, selling price, right? So in selling price, if you look at this, look at either the row or the column itself. So say sales in thousands, if you can see, which is not correlated, this 0.088, that is very, very poorly correlated. What is that? Engine size. Okay. Ideally, for this data, it is not correlated. That's what. Ideally, it should be correlated, because bigger engine means it's a bigger vehicle, means bigger price. That's how it should be. But in this case, it's not correlated. Okay. So you can ignore such features. I mean, in this case, if you see, none of the features are correlated. I mean, not very well, except for this 0.3 and 0.2. But in previous case where we have seen the correlations, so as you can see here, kilometer drivens had a direct impact. If you see this selling price, second row, look at only the second row. Selling price has a direct correlation. 40% of the time it has correlation with the year. That means manufactured year, 40%. Selling price is again has the correlation with kilometer driven, but only 20% of the time. This feature, selling price, has very less, negligible correlation with seats. So seats has to be removed. Straightforward. No need to even think. Okay. Next is selling price also has a good correlation with max power. But again, max power has to be, then you will have to go back to max power column and check which are the other features that it has correlation with. It has correlation with engine. Max power has correlation with both selling price and engine. Now you have to decide to keep whether engine or max power. Okay, that way you can in a very simple way, you can come up with which features to keep, which features to drop. Okay, so once you decide this, okay, whichever features are showing correlation, like in this case, the feature max power is showing correlation with engine. Hence, we call it multi-collinearity. Okay, multi-collinearity. Okay, that means multiple features are correlated linearly. Okay, so that means there is no point in keeping multiple features which have correlation, simply because they don't add any value. Okay, if one feature is able to predict my target, why do I need another feature that does the same task, right? So that has the same information, same correlation. That's what. So that way you can get rid of this. Multi-collinearity can also be measured using something called variance inflation factor, VIF. Okay, so this VIF will tell you how much of effective multi-collinearity is there. Okay, for example, horsepower and VIF, if you can see, 218 is there. Okay, so these are the columns, wherever the value is high, there those columns are showing multi-collinearity. Now you have to decide which one to keep, which one to drop. For example, horsepower or engine size. Okay, this way you have to decide. Okay, for multi-collinearity, here we are only detecting. Now we will start, whatever we have done the steps, we will start implementing them. Okay, we'll get rid of all this. Next, splitting the data. Okay, next step is, after you're done with the encoding process, sorry, not the encoding, the feature selection. This is one way to do. One is correlation, another one is VIF. There are multiple other methods called recursive feature elimination. Okay, what you will do is, you will use, in first iteration, you will use all the features to do the modeling and see the feature importance. Whichever feature is showing very, very minimal feature importance, you will remove it. And then you will rerun the algorithm again by removing the first feature which showed no importance. Again, if one feature shows less feature importance, you will remove that also. Then run the third iteration, fourth iteration, fifth iteration. This way you will run multiple iterations until you are satisfied with minimum number of features that can be kept for final iteration. Okay, so that is also one of the methods called for feature selection. Okay, is this clear up until this point?
Yes.
Okay. Yes.
Okay, all right. Next thing is, in this scenario, see, it is always best when you are working with linear regression. I would recommend that you run these three: multi-linear regression, okay, lasso regression or ridge regression. I would also include elastic regression and Huber regression. Okay, not just these three. I would say a person who is working on a linear regression algorithm should run all these 5 algorithms in one go. The reason being, if there is some sort of overfitting here, okay, you can see the improvement immediately in lasso and ridge. And elastic is a combination of lasso and ridge. Okay, I will explain you what all these 5 are. Okay, all these 4 are. Okay, and you can immediately see the improvement in elastic or Huber regression. Okay, so this way I recommend a person immediately runs. I mean, whenever if you are asked to use a linear regression, you have to use all these 5. That is what the understanding is, because all 5 work on the same principle with minor changes only. Okay, so that's the thing. Okay, in order to use this, now that we have identified which features to remove, finally we have to divide the data. How are we going to divide? Is we are going to call, see, remember the multiplication x and y matrices. So x is what has to be multiplied with something to get y. Okay, and this m is what you are trying to get. Ignore the c, because c is very negligible usually, so we don't worry about c. But you also have an option to keep c if you want. That I will show you. But usually to get m, you have to have x and y. Now x is nothing but all your columns that other than your selling price, and y is only the selling price. So that is what you see here. And another important thing is you have to keep them as arrays. Okay, so they have kept it as arrays here, no? So if you, in NumPy you have an option, if you just add dot values, it will convert the complete data frame into two-dimensional. 2 brackets means two-dimensional, simple. Two-dimensional array. It will convert it to two-dimensional array. So you can confirm that here also. Two brackets. Again, y will be one-dimensional only. Y will be a array of one-dimensional numbers. Okay, or a vector in other words. So here again another mistake. After you divide the data, the next thing is it has to follow this order only. First x should come, then y should come. You should not write x train, y train, x test, y test. Okay, that is another mistake made by beginners. So you have to ensure only x comes first, then y comes first, and then you already have a method called train test split where you can pass x and y. Here either you can specify training size or test size. If you're going to specify training size, you can specify 0.8. If you're going to specify test size, you are going to specify 20% of the data, and random state you have to set, because in order to obtain the same results by other colleagues or by management, if they want to review, you have to have the same random state. And shuffle equals to true. Why shuffle equals to true is these values rows while feeding to the data has to be fetched in random order. So that's why shuffle has to be set as true. Okay. And shuffle equals to true also does one more thing. While selecting this test size and training size, it selects randomly. Okay, so that is main thing. Okay, now you will apply the linear regression algorithm. While applying the linear regression algorithm, you can calculate the metrics. So by doing all these, what all the changes we made from as compared to previous thing, we did transformations that we didn't do previously. We didn't do transformations here. That is one fatal mistake that we did. Second thing is we did scaling also, right? And third thing is outlier treatment also we did. Previously we had not done outlier treatment. That's why our results are very, very poor. And feature engineering. Okay, feature engineering is fine, but these are the main things: scaling, transformation, outlier treatment, encoding. Okay, so these are the things that will help you get the better results. Now that you, after doing all these steps, when you apply the algorithm and do the prediction, you can calculate mean squared errors, root mean squared error, R2 square, right? So now you can see better values. R squared value previously was 74, now it is 92, okay, 0.92. And root mean squared error of the model is very, very low. This is beyond belief, to be honest. Very, very good number, okay. So that means, what it means is, out of 156 rows of data, if the model gets similar data, then it will predict. Again, these numbers are in thousands. Selling price is in thousands, right? That means either it will make mistake, it will only make mistake or deviation of 4245 only. Okay, if you multiply it with 1000, you will get 4245. That means if you try to sell a car, okay, you will not lose huge amount of money. Okay, worst case scenario, you will lose 4245. Okay, and with your tricks you can earn more also, but you will not lose a lot of money. You will make only 4000, you will lose only 4245 rupees, okay, than the average cost of the selling price of the car. Okay, that is what it is. So the error rate went from few lakhs to 4000. So that is a good number. Okay, so this way you can apply the linear regression. Now coming back to lasso regression. Now lasso regression, what it does is, so while calculating the okay, let me open the, so while calculating the error rate, previously we saw the error rate that it calculated. Error rate was the difference. Let me, I think I have that window, 1 second. So there was an error rate, no? Error rate as in the difference between the actual points when you plotted on a straight line. There was some difference between the actual points where they were and where the model predicted where the model placed the straight line. Okay, this one very, very important. This I anyway want you to know. This is for logistic, I think. 1 second. Okay, this is for logistic, not this one. There was one for linear regression as well, wherein which, yeah, I think this one, yeah, this one only. Okay. So this is what it was, right? So this is how the points are aligned. The error is nothing but the difference between the average distance between these points and the line, plotted line. We want the line to be along these points only, so that the error so that the difference between those points and the line decreases. That is what the loss function is. Now, what lasso does is, instead of only calculating the difference straight away, it will add additional penalty term. It will further decrease the loss by minimizing the distance between these points. And to that minimized distance also, again on top of that, it is adding additional value to decrease the loss. Okay. So lasso regression, okay, let me see if, okay, not here. So lasso regression, second, okay, maybe it's not there here. Okay, so basically lasso regression adds a absolute value of the another absolute value of penalty term. Okay, one second, let me see if I can pull that interactive. There was one. Sorry. Okay. So you already had the sums of the squares. Okay, that is the difference. Mean squared error was the difference. That is whatever the actual value as y minus predicted value y cap. You are already doing that. But what lasso is doing is, to sum, it is adding some amount, this lambda, I will talk about it. It is multiplying that lambda to some absolute value of the coefficients. So what it is doing is essentially it is decreasing every time you multiply this number. It is decreasing the impact of coefficients on the feature. Okay, let me, okay, just, yeah. So basically you had m and then you had x. Okay, then you got then you also have y, right? So here, I mean, if you understand it once, it will be very easy. This is m, right? This is m, and then you had x, and then you had y. Your job was to get to y by multiplying these two, m into x and y. Now after multiplying, you learned on 80% of the data you learned. Okay, you learned some m values. Now your job is to use those average of these m values. Okay, now on the prediction part, your average of m you will use multiplied by x to get y cap. Now you know m, that which you have learned from here, and you're going to multiply with x and you're going to get y cap. Now what lasso regression is doing is, it's impacting this. See, in earlier case, how is the loss calculated? Y minus y cap. Okay, and then you can take the square. If you want to take, you can take the square also. Again, it depends whether you want to go with the absolute difference, or whether you want to go with the percentage difference, whether you want to go with the square difference, or root mean squared also you can go, whichever your choice is. This is how loss function was being calculated. Okay, and let's just say this value was 10, this value was 5. 10 minus 5 is 5. 25 was the value, initial loss value. Okay, now what this lasso regression is doing is, it is adding additional penalty to that loss. Okay, so if you add additional some value to the magnitude of those coefficients, what will happen? What will happen is, it the actual value of the, while training, see what happens. So this was all done during training, right? Now what you're gonna do is you're gonna add additional value here. Let's just say you added 10. Okay, you added 10. Okay, just understand the process. If you understand the procedure, you will understand what I'm trying to say. So in the first row, when the first row of values was fetched, m1 was not known, certain x values were known, y value was known. You got m1 by sending this other side, you x inverse into y, you will get m1. Okay, when you got m1, okay, you calculated y minus y cap and it turned out to be 25, and likewise you calculated for all the rows, took the average, you got some value. This is normal regression. Clear? But what see, basis on this calculation, what the algorithm is trying to do is, it is trying to essentially only adjust. See, this is the, if these are the points, it is only trying to adjust this line. Okay, if the error rate is high, it will adjust little bit, it will change the m value, maybe it will change the line here. Okay, but what lasso is doing is, it will additionally adding the loss, adding the penalty to the cost function, to the loss function. Once it adds more penalty, now each time it adds the penalty, the model is thinking, whatever I have calculated the m value, it is not the best fit line, let me recalculate. Then again it will go and recalculate. Okay, so it will arrive at the best fit line quicker. That is one. Second thing is, while doing the training, the m value that it has calculated, because this penalty term is added, what model is thinking is, this m value that I have calculated may not be correct. Okay, so it has to be decreased. Maybe it has to be further decreased in order to fit the line properly. So this m gets decreased. As the m gets decreased, okay, when you do the multiplication on the inference, you have calculated this m average. Because these m values are low, the average will also be low, and when you multiply low average with x, this y cap will come very nearer to approximately equal to y. Are you following me?
Yes.
Okay, that is one. See, first thing is, it is adding penalty to the cost function, making the model think that the best fit line is not the best fit line. I have to recalculate, and m values are recalculated, and because m values are recalculated, average becomes low, and when average becomes low, y cap comes closer to y. That is one. Okay, and the second thing is, because m values are low, see, what are m values? If you do this multiplication, it means if you are talking about height, so let's just say height is multiplied by m1 plus m2 is multiplied by weight to give you some, whether a patient is diabetic or not. Okay, D or ND. Okay, let's just say this is one example. Now because m value decreased, this entire term becomes, if this m1 becomes closer to 0, this entire impact of this entire term becomes low, no? 0, anything very small value multiplied by bigger value will be smaller value only, right?
Yes.
So the impact of this on judging whether a patient is diabetic or not has decreased now. Okay, in other words, the impact of second feature has increased. Okay, see, if 2 plus 3 equals to 5, simple, in very simple math, 2 plus 3 equals to 5. If 1 becomes 0, the other has to be 5 only. Correct? 0 plus 5 equals to 5. Do you agree? If the impact of one feature has decreased, the impact of other feature automatically has increased. Now the model, what model has done is, just by adding this penalty term for each calculation, what we have essentially done is, we have penalized one of the features wherever the lasso regression has penalized the features where the coefficients were low, thereby highlighting the most important features. Okay, so are you following me?
Yes, yes.
Okay.
So this will be applicable only for the multicollinearity, right? I mean, for the single feature, it won't be applicable.
No, it is applicable at single feature only. No. See this matrix multicollinear. Okay. I think I understood your question now. Yeah. It is applicable for all the features, because in the X you have all the features here.
Right.
Okay. How is dot product done? M1 into first value.
Yes. So because we are actually trying to penalize one of the feature by and ensuring that the impact of the other more relevant feature is increased there on the prediction.
Yeah. So just by increasing this penalty term, two things are happening. One, it is able to decrease the impact of less important features. Two, the best fit line is calculated in a much better way. Okay.
So this decision of what penalty term should be added is it the data scientist has to decide, or the algorithm itself is
correct. Good question. Yeah. So what should be the penalty term is automatically decided by the algorithm. It's not something that we set. Okay. So in this case, if you see, we are just calling the lasso. Here we are just checking for different learning rates. Okay. But if you notice, we are not setting anywhere what should be the value of the penalty. There is no penalty.
Okay. Is it that with these learning rates, we are trying to find out the best fit line?
Yes. So I think we talked about this in the concept of gradient descent. Okay. What happens
I will refer that. Sorry. I have just missed those lectures, so I'll just go through the recording. Sorry for that.
Yeah, please. I mean, you're free to ask the question. So if you don't understand, please feel free to ask. Okay. It's not like there is no compulsion that I won't repeat it. So it's not like that.
So, Sadiq, is this the difference between different algorithms, or apart from this, like how they calculate and how they reach to the best fit line?
So there are, these are the variations of the same linear regression algorithm. Okay. But there are multiple other algorithms in the way how they calculate is also entirely different. Okay. So this is just the one variation of one single algorithm.
But in mostly in the linear regression, we will have the gradient descent only.
Yes.
Backend.
Yes. Backend mechanism is same as what we have discussed already. Okay. The learning rates, you remember we had plotted one U-shaped graph and we were trying to see.
Yes. I remember. It's the fastest way. It should not be going from one side of the line to the other side of the line. So we have to adjust the learning rate so that we reach the lowermost or the bottommost point at the earliest. I remember.
Yes. Yeah. So we are experimenting with multiple values here. But otherwise, we don't set any penalty. Penalty is automatically handled by our model. Okay. When you do the prediction and calculate the numbers. Okay. Now, in this case, although the numbers decrease 0.926, here we got lesser number 0.924. Okay. Although the value decreased, maybe because less number of rows are available for it to actually make any difference. Okay. But otherwise, if you have huge amount of data, this is a recommended one. But one thing for sure has happened is that if you calculate which are the features that are contributing to it, okay, then you can see that we will see in another class how to implement Shapley and all of that. But when you calculate the feature importance, you can see Lasso has done a better job of highlighting important features. and diminishing the impact of less important features than the normal regression. That is for sure. Okay, so that is the change. Now ridge regression, very minor difference between ridge and lasso regression. Now instead of adding an absolute value here, okay, you are going to add a square term. Okay, let's just say you will add 5 square only. Okay, you will add 5 square, thereby making the value 25. Even more penalization. Okay, so more impact. So that way, now see, with ridge regression, again the values are back. So basically, ridge regression and lasso regression will add the absolute value of the penalty to the coefficients, whereas ridge regression will add the squared term as a penalty to the coefficients. That is the only difference, but otherwise they are same. Okay.
So
the entire process of
how are we comparing the performance of these three algorithms here? I mean, what will be the basis of comparison?
We are calculating R squared.
RMSE.
Yes.
Okay.
Yeah. RMSE and R squared. Okay. Ignore the support vector regression. We will talk about it another time.
So lower is RMSE, better is the model. And
no.
How do we?
Correct.
R squared. How do we? Use the R squared for that? Is it the same way that lower is the R squared? Is it also the error? Is it RMSE based? I mean, R squared?
No. R squared is how well your model is fitting the line. Okay, by decreasing the error term.
Okay, so fine. Okay.
Yeah.
You might have discussed it earlier. I'll go through that. No problem.
Yeah. So R squared, what it does is it looks at the variance of the features and tries to explain how well the best fit line has captured that variance. Variance is nothing but the different points wherever they are allotted, right? Range of. Okay. So now what R squared is telling.
Less is the R squared, better is the model.
No, R squared should be higher.
Higher, okay.
Our model should capture highest variance possible. So higher the variance, better the higher the R squared, better the model. Lower the root mean squared error, better the model.
Better the model. Okay.
Yeah. So that way. So these are the things by which you can calculate, and if we calculate the same things here as well. 1 second. I think we can quickly do this. Okay. I'll take the same thing. Test for homoscedasticity. If you do these calculations also, okay, you have, let me check if it is y test only. Y underscore test, y underscore pred. Okay. So if you do the very quick calculations, you should be able to see that this model has performed far better than what the other previous model did. Y pred and y underscore test and y underscore pred. Okay, so if you do this, we need to check what we have written. Y pred, is it y underscore pred? I think this is what we have written, no? Okay, capital P, maybe. Capital P. Okay. So now you can see, so in our previous case, it was a funnel shape. Funnel shape means heteroscedasticity, which means it is bad. Okay, we should not get this funnel shape. Rather, we should get a more like a either random or along this line. Now we can see the values are along this. We are not seeing this type of shape here. It's not going like this, no? So this is far better than what, maybe not perfect, but it is still better than what we previously had like this. This should not be the case. Likewise, you can check for others also. You can simply calculate this. Okay. This test we did, we looked at LM values, right? We should not get higher LM statistic values. Okay. So this you can confirm right here. If you calculate like this also, you can get it x underscore train, and then constant model. So if you, okay, now you see LM statistic, previous LM statistic was in thousands. Okay, now we have much better statistic, lower value. Okay, it is not perfectly homoscedastic. Okay, but it is far better. That is what we are trying to make the conclusion as. Likewise, you can also look at the QQ plot. If you look at the QQ plot of residuals, maybe you can get better idea. Okay, so although it is still not aligned, it is we are still not seeing the normality of the residuals, but at least it is not a vertical line. It's kind of going in this direction. Okay, so I think we can make further improvements on this. If we apply a Huber regression, we can make further improvements on this also. Okay, at least it's not like one straight line here. This is like very bad. Okay, and even the quantiles, if you see quantile range, you can see that is also differing. Here it was at 0. Here there is some slight tilt. It's not exactly at 0. It's going from other direction. Likewise, you can also calculate the Cook's distance if you like. So I don't know, it's stuck. Okay, so like this, you can also calculate the Cook's distance. I'm sure that also will be far better. There won't be this much variation. Leverage will be less. So this way we can say our model has performed better. Okay, and the final conclusion is linear regression can perform better if there are no missing values. Outlier treatment has been done perfectly. Features have been correctly selected. Skewness handled. Distribution has been handled. Multicollinearity has been handled. Okay, so all these things should be met. And one recommended thing for you is, if you can't go through this entire thing, it's okay, I understand, but at least this month, at least I want you to go through this link. This link I have already attached. Very beautiful explanation. I think we can't explain linear regression better than this. So this guy has done a very good job. I want you to just go through and understand it. Okay, that would be it for linear regression. This completes linear regression. So ridge and Huber regression I will show you, but more or less this completes all the regression part of it. Okay.